How does a skateboard pull off awesome tricks and survive battering blows? What's at the heart of a vacuum that helps it suck carpets clean? And how does an ATM deliver exactly the right cash hundreds of times a day? To answer these mysteries, we dive deep inside these and other extraordinary machines to reveal the secrets of how things work. ATMs. They deliver the money that makes the world go around. But how does an ATM make sure it hands out the right amount of cash to the right people? 400 parts work together. A smart card reader that checks your balance. 2 secure vaults that can hold 3,000 bills. High-friction rollers that pick just one note at a time. And sensors that spot when a second note slips through. Super strong welds fuse together a 220-kilogram steel case to keep the cash safe and ready to flow. At the heart of the ATM is the control panel that matches your PIN to your bank account. These machines operate inside as well as outside in booths, so it's crucial that their smart electronics work even if they're exposed to the rain. The secret to the electronics never failing is the way that workers in this Mississippi factory put the machine together.
You want to make sure that you get your PIN right on the keypad if you want any money.
Liz builds the control panel by hand. She starts with the machine's 38-centimeter touchscreen display.
The main board is the brain of the ATM unit. It's where all the components come together at.
Liz's priority is to protect the ATM's sophisticated electronics from shorting out in wet weather.
We want to make sure it's seated in nice and tight. Don't want any moisture getting through.
Liz plugs the card reader and keypad into the main board.
It's very important that we ground the right components. There can be a lot of issues with different components shorting out from the weather. We don't want any moisture to get into it because when the main board shorts out, anything can short out.
She then fires up the control panel and calls up the banking network to check that the electronics can talk to the outside world.
The ATM contacts the bank says yes or no if you have money in your account. It sends the word back, and then either it dispenses your money or it tells you, no, you can't have it, and you hadn't been paid yet.
The ATM's card reader and motherboard act as gatekeepers between the public and their bank accounts. Once they verify a PIN, the machine must deliver the right number of notes at breakneck speed without a rip or a jam. This is how it does it. Deep in the heart of the machine, 2 steel cassettes hold over 1,000 notes each. A serrated rubber roller kicks up 1 note from the stack to a pair of smooth rollers that feed it onto a conveyor belt. A sensor checks that notes never double up. So this robotic teller can spit out up to 5 notes every second. Different countries' currencies come in different shapes and sizes. So the ATM must store and remember the dimensions of each kind of cash.
We send these mechs all over the world: Australia, United Kingdom, South Africa.
Dan installs the mechanism that delivers notes to the customer.
Not all currencies are the same size. I have Mexican pesos, Australian, South African,
He sets the note's width and height, and the machine learns the note's thickness.
And now I'm ready for it to start learning the bills that it'll be dispensing at its final home.
An optical sensor measures the thickness of each note, which varies from country to country.
Right now it's running bills across the sensors for note thickness. It's learned it, now it's dispensing them.
This way, nobody will ever receive an unexpected windfall.
Our customers wouldn't be real happy about giving somebody $40 instead of $20.
An ATM can contain up to £150,000 in cash. How does it keep the cash in the safe, but make it easy to refill when the money runs out? Under the skin of the ATM is a 220-kilogram box. Its walls, 1.3 centimeters of solid steel. The door has a super wide bolt that runs along its edge. The only way in, a keypad with 1 million combinations. It rotates to release a deadbolt. So the handle can swing an aluminium pendulum to pull back the bolt. It's like Fort Knox in a box. These features mean that potential criminals face a real mission impossible. Before each machine hits the high street, Nancy puts them through a rigorous safety and performance test.
To me, it's a challenge to keep up. I like being fast-paced.
She checks the cabinet's insulation to make sure it won't deliver a nasty electric shock.
You want to give a quick inspection, make sure everything's plugged in. You don't want anything to short out or arc out when it's out in the field.
Each machine must then perform 200 transactions to confirm that it can talk to the bank and deliver notes without a hitch.
If something's going to go wrong, that's when it's probably going to go wrong.
Nancy collects the cash as it drops in the bill trays and makes sure the paper receipts don't jam. The 6 machines here churn through 1,200 transactions an hour.
After a while, you just kind of tune them out. They don't really bother you at night. You don't hear them in your dreams or anything like that.
Smart design and innovative engineering mean 3 million ATMs across the planet can dispense billions of pounds a day. This machine keeps pockets full of cash and the global economy turning. The vacuum cleaner. It removes dust and dirt with every sweep. How does this machine generate storm force suction in a pod that's light enough to haul around the house? 85 parts work in unison to generate maximum suction. A bag that lets in the air, but locks away the dust. A steel propeller that spins faster than a power drill to suck in 2,000 liters of air a minute. A super efficient motor that uses less than half the power of a hairdryer. It's a dust-hungry beast that's designed to last. Together, these components create the vacuum's ferocious appetite. The body must be airtight for good suction, but also accessible to throw sucked-up dust away. The secret to the cleaner's super suction is the factory's ingenious injection mold that squeezes the body into shape.
These are little tiny plastic beads. When I first came here, I thought they were like tiny little white marbles.
Ian's job is to make sure that each mold squeezes together exactly the right proportion of plastic beads.
It's all done on vacuum. You can hear it kicking in now. One of the machines is cooling.
If Ian gets the numbers right, the cleaners should be perfect. Get them wrong, and hundreds will be destined for the dustbin. A vacuum cleaner needs an airtight drum to suck up dust. The secret is to make a plastic mold with a leak-free seal. So Ian uses injection molding machines to create an airtight body with ferocious suction. Sensors call in the correct volume of beads, which the mold melts and squeezes together.
So they get fed in, and then when they get the injection unit, then they are turned into molten plastic under high temperatures, about 180 and 220 degrees, around that area.
Two molds form the drum unit, a base that holds the dust bag and a lid that holds the motor. A rubber seal makes sure that the joined-up unit is leak-free. The perfectly sealed body gives maximum suction. But what stops the motor from overheating inside it? This machine has a clever design to keep cool. The 620-watt electric motor sits on top of the suction fan. As the fan blades spin, they push air up towards the motor, keeping it cool even on full blast. At the other end, the airflow pulls in the dust, and a bag with tiny pores traps it safely inside. That's how this machine can clean your house without ever getting hot under the hood. For a vacuum cleaner, keeping cool is second nature, but the dust it devours could easily put it out of action. So the workers who build them must make sure that dust and motor never meet. They fit a bag and filter that catch the bulk of the dirt. Then they fit the motor into a dust-proof casing.
If there's not a good seal, the suction would be no good for vacuuming anything up at all.
Kevin checks the motor of every cleaner that leaves the line.
Just want to make sure the seal's nice and tight between the drum and the lid.
This cleaner sucks fine. The motor generates a constant 160 km/h stream of air that sucks dust up from hard floors. But on a thick pile carpet, even these hurricane-force winds won't do the job. So how does the cleaner suck up dust that's ground deep into a woolen pile? Hidden inside the brush head, this machine has a secret weapon. A small turbine whirls in the airflow. A rubber drive belt connects it to a spiral brush, whose bristles kick up even stubborn dust. This turbo brush head spins at 5,000 times a minute to give maximum cleaning power. This little machine can deal with a talcum powder Armageddon. Before each new model hits the showroom, it must get through the Vacuum Olympics.
We're in the dust pickup lab that's air-controlled in temperature and humidity.
Chris puts the cleaners through their paces in this £500,000 vacuum testing facility. Robots stretch the hoses and spin the cleaners by their cables to guarantee the machines meet the gold standard and won't fall apart. The machine's final challenge is to suck up as much dust as possible from this test carpet.
We put down some Norman sand, which is some very expensive dust, which is required for everyone who's doing dust pickup tests to have.
This standardized dust allows Chris to check how good the cleaner is. To meet the required standards, the cleaner must suck up enough dust from the carpet.
So now we're stopped, we're just going to weigh the bag to see how much dust he's picked up. And that's 63.09.
This cleaner makes the grade. It's good enough to keep even the thickest carpets pristine. Vacuum cleaners have been sucking carpets clean for over 100 years. They eat up millions of tons of dust and make rooms the world over just that little bit nicer. The skateboard. Great for ollies, slides, and kick flips. All awesome tricks, but all brutal on the board. So how does a deck that takes such a battering deliver such a smooth ride? A gritty silicon carbide surface grips like sandpaper. 7 layers of hard rock maple make the deck tough to bust. Rugged aluminium trucks that can turn on a dime. Wheels that land softly without losing their shape. And precision ball bearings that can take a beating but stay silky smooth when the ride gets gnarly. These components form a strong, fast, and agile board. But how do layers of maple, just 1.6 millimeters thick, make a rock-hard deck? The key to the board's strength is the way that workers at this Santa Barbara factory assemble it. The boards made here are used by some of the world's best skaters. And for the past 14 years, Mario has honed the skills needed to make them so tough.
We use Michigan maple. Gives more bounce for the skateboarder.
Mario glues together 7 pieces of wood, called veneers, to make a robust deck. He alternates the direction of the wood's grain to make the deck flexible but strong.
So you got strength going one way, and you got some strength going this way. So it makes the strength going both directions.
Mario then squeezes the glue-covered veneers together for 45 minutes in an air press. The press bends the flat deck into a board that kicks up at either end.
Kicks give the board that extra pop they need so they can land the trick or do the trick well.
A router cuts the boards into shape. Then Mario sands the edges for an ultra-smooth finish.
We do it so we can protect it from splinters, protect it from breaking, chipping when it hits cement, street, or anything like that.
The multi-veneer deck is strong enough to hold up against even the most adrenaline-fueled skater. These tricks don't just demand a board with strength, they also call for lightning-fast handling. Tucked away under the deck is the board's business end, the trucks. Cast as a solid block of industrial-strength aluminium, they grip soft polyurethane shock absorbers for radical twists and turns. Inside the wheels, 7 hardened steel balls run in a nylon cage, cutting friction to almost zero, to make a board that's silky smooth, but tough as nails. Skaters rely on hard-running, bouncy wheels to pull off awesome tricks. The key to a bouncy wheel is the way that workers make them.
We're looking for the highest rebound, which will give us the fastest rolling speed of the wheel.
Jesse's job is to bake the wheels. He pours a top-secret combination of chemicals into a mold. He also pours a test ball to check the whole batch for bounciness.
I'm gonna make 2 balls so that I can check the rebound of each set of wheels.
Jesse bakes the molds for an hour to create wheels with maximum rebound. The timing is crucial. Bake the wheels too hot and they lose strength. Don't bake them long enough and they come out like mush. The skateboard is a piece of ultra-strong precision engineering. To execute its awesome tricks, it needs wheels that bounce. The crucial step is the baking process. If Jesse bakes the wheels too hot, they lose strength. If they don't bake for long enough, they'll lose their shape. The team pop the wheels free and spread them over the floor to cool overnight. It's then just a simple check to make sure the wheels are baked to perfection.
This is a test ball that we made with the same material. The higher the rebound, the faster the wheel's gonna go. So, as you can see, we have a good rebound on this test ball, so it's gonna make some pretty fast wheels.
The skateboard's wheels race along the tarmac and spring the deck high into the air. It's smart science carried off with serious style. The car jack. It can lift heavy vehicles using nothing but hydraulic oil. How does such a small machine pack such a powerful punch? 240 parts work together. A steel frame that can take a beating in the workshop, a hydraulic cylinder with a high-precision piston generates 5 times the pressure of a car crusher. A load-limiting valve that yields before the jack can lift unsafe weights, and a sturdy lift plate to support 6 tons without bending. It's 115 kilograms of pure lifting power that can bench press a Hummer. Huge forces put the jack's metalwork under serious strain. How does the car jack punch so hard above its own weight without bending out of shape? With mechanics' lives on the line, it's crucial that workers in this Missouri factory construct the jack with welds that are up to the task.
So if these welds don't hold, we could have a 12,000-pound vehicle coming down on somebody, and that's not a good thing.
A 6,000-watt laser cuts through sheets of steel to create the pieces for the jack's frame. Trevor's mission-critical job is to weld these pieces together.
This is where everything happens. This is the most important place of the shop.
A robot welds most of the joins with extreme speed and precision. But Trevor must check every piece of its handiwork.
Now I'm gonna make sure that every weld that robot put on is exactly the way it should be. And weld what the robot couldn't reach. This is gonna be your lift arm. The only thing it'll need to be painted and the hydraulic power unit put in.
A coat of spray paint creates a rust-proof finish, and the jack's metal frame is ready to get to work. The metal frame doesn't lift up cars on its own. It relies on a clever 20-kilogram device to provide the power for the jack's heavy lifting. Each stroke of the jack's arm moves a small plunger. It draws in oil and squeezes it into the main cylinder. This pushes the hydraulic cylinder's main piston shaft 2 millimeters with every stroke. This drives a scissor mechanism, which lifts the car. It's a simple design with a mighty punch. The hydraulic cylinder is the jack's powerhouse. The tough metal shell squeezes hydraulic fluid down to more than 9,500 pounds per square inch. As Brandon constructs the unit, he must make sure that this liquid can't leak.
If anything on this jack leaks, it will eventually lose pressure, just will not pump up correctly.
The base starts as a steel block. Computer-controlled drill bits cut channels for the hydraulic fluid to flow through.
This one looks excellent.
Only ultra-strong metal balls can control the flow of this super high-pressure fluid without deforming.
The ball that we use in these blocks is actually harder than any steel block that we manufacture.
Brandon checks the block for debris, then rams the balls home so they sit nice and tight.
We put the balls in and now we seat them to get a good, tight seal.
He builds the hydraulic cylinder up from the base block.
You got O-rings that seal the reservoir onto the block itself so it does not leak.
And screws the cylinder sleeves into place using some serious torque.
This tool here fits over the top of the cap. The motor in the bottom of it will actually spin the base, hold the cap in place, tightens it to over 600 PSI.
The jack's hydraulic unit is now primed for pumping and ready to push up extreme loads. But how can a mechanic underneath a 2-ton truck be sure the jack won't give way under the pressure? Tucked away deep inside the jack is a fail-safe. It's a small but powerful steel spring. It pushes against a metal pin that plugs the hydraulic pipes. If the load is too heavy, the pressure rises and the spring yields. This diverts the fluid away from the cylinder and into an overflow system. So no matter how hard you pump, this jack won't lift a finger. To lift the vehicle high enough to slide in the essential support stands, it's critical that both the hydraulic unit and the lift arm can hold the vehicle's weight. Failure is not an option.
If it fails the test, you will know, believe me. You'll hear a loud bang, oil will blow out of the bottom of it.
Dan pushes every jack that leaves the factory to its limit. Each jack must fully extend its lift arm against a 6-ton hydraulic test rig in less than 6 minutes.
If it doesn't pass the structure test, it goes back, we tear it apart, we fix it, and we do it again.
Only jacks that meet these tough standards leave the factory doors.
This jack is good to go.
The car jack delivers serious lifting power. Its tough components and smart design make the lightest work of even the largest SUV. Digital projectors. They create dazzling images with incredible resolution. But how does a projector, without any film, produce a moving image? 500 parts work in unison. 175 lasers blast out light beams. A column of ultra-pure glass collects the light. 3 special chips create a pin-sharp 8.8 megapixel image. 3 kilograms of flawless glass lenses blow this up to the size of a bus. while 3 different cooling systems soak up the heat. So this machine can shine without a bulb in sight. The lenses in this projector magnify the image over 1,000 times, exposing even the tiniest flaw in the system. So every single piece of glass inside the machine must be spotless. Workers in this factory in Manchester, England, where the technology was first developed, must assemble the optics with incredible care.
One of our main enemies is the dust.
It's Eamon's job to install the projector's optics. A near-perfect glass prism, a faultless lens. And at the heart of the projector, inside a protective metal casing, an 8-centimeter column of ultra-clear glass. Its job is to gather the light from the lasers to produce a perfectly uniform image on even the largest cinema screen. That's why it has to be extremely clean.
You could think of something as small as an ant's footprint. That would be a large image distortion.
If Eamon doesn't get the glass crystal clear, thousands of pounds worth of optics will be useless. The digital projector is a true marvel of the information age. But just one speck of dust on the glassware could ruin its image.
We need to keep all the optics clean. Assembly has to be in a clean room.
Eamon works on the glass column under a pressurized hood. This pushes out highly filtered, ultra-pure air, almost completely free from dust.
I'm looking now for microscopic contaminants. This one has a small amount of dust on it.
With the glass column crystal clear, Eamon mounts it on the optical assembly and fits the projector's 5-kilogram lens. The ultra-clean glasswork that guides the projector's light is now in place. Now this machine has 12,000 lumens of light available, brighter than the headlights on a jumbo jet. But how does it turn this raw firepower into detailed, colorful images with nearly 9 million pixels? That's when this massive machine needs microscopic technology. At the heart of the projector, a high-precision prism splits white light into primary colors and then beams it onto 3 microchips. On their surfaces, 8.8 million mirrors, smaller than a pinprick, flicker on microscopic hinges to split up the light beam into 8.8 million pixels that form a moving image. The prism merges the light from the 3 chips to produce 281 trillion shades of color. Workers must make sure that the chips line up precisely to work their magic.
You can't try and do too much at once because it will just make you go a bit crazy.
It is Mick's difficult job to carefully position the chips. He places each chip onto a separate face of the prism. This way, each chip reflects a different color.
You've got the red will be overlaid onto green, green will be overlaid onto blue.
Mick must line up the images from each chip to produce a crystal clear, multicolored image.
So what we do is we turn the lights off and then we start adjusting.
He monitors the position of each chip using the 3 overlapping grids they project. 1 in red, 1 in green, and 1 in blue. He then uses precision screws to adjust the position of the chips and make the grids overlap.
You can see that we've got green pixels there and blue pixels here. So I'm trying to get them blue pixels right on top of those green pixels.
Mick's got the blue and the green grid aligned. It takes a few more tweaks to bring the red grid in too. Now all three are in perfect alignment.
That looks to me as though that could go into a projector.
The projector consumes 1,600 watts of power and generates intense areas of heat that could ruin the projector's image. So 105 metal spikes draw heat from each of the chips. 1 meter of metal tubing pumps 2 liters of liquid coolant to chill the banks of lasers. And 19 fans, spinning at 3,000 times a minute, expel enough heat to boil a kettle. So this machine can show movies without going into meltdown. This efficient cooling system allows the projector to screen thousands of movies before it needs a service. Every one of these films should look the same in every theater. So workers must match the projector's colors to industry standards.
So what this does is it measures the light intensity.
Before it leaves the factory, Alex tests the projector to make sure its colors are spot on.
The greens, the reds, the blues can be slightly different. So what I'll do in here is correct that.
Alex measures the precise combination of colors that add together to produce the projector's green.
We've taken a reading from the projector's green.
This information lets Alex slightly tweak the projector's hues to create an image that's picture perfect.
I'll introduce maybe a little bit of blue, a little bit of red to allow for this green to come back down into the industry standard.
Alex repeats for blue and for red, and this projector's ready for showtime. Thanks to decades of technological innovation, digital technology produces high-resolution moving images that even film can't beat. The multi-tool. It's a toolbox that fits in your pocket. One tool that does more than just one job. How does this 240-gram piece of metal transform into so many different tools? Under a tempered steel frame, 17 different tools deploy with a simple flick. 3 sets of safety tabs lock them into place. A clever hinge holds the tools together and allows for a trademark transformation. From a multi-tool to a pair of pliers with a flick of the wrist. 17 different solutions to thousands of different problems. The key to how so many tools squeeze into the multi-tool's 10-centimeter handle lies in the incredible machine that assembles it in this Oregon factory. The machine performs 16 punches and folds to produce a perfectly shaped handle. Each blade and tool pivots into the handle with dimensions exact to within 1/20th of a millimeter.
This is what I love to do, and then it's fun, yeah.
PAC has kept this machine running for the past 20 years. Just one stray lump of metal debris could ruin an entire batch of multi-tools. So he constantly listens out for unusual noises.
Because I've been doing it so long, I can tell what's wrong by the noise.
Pack checks one handle in 500 to make sure they're the perfect size.
This red thing right here, make sure it's not going in. And this green right here, make sure they go in smoothly.
If just one measurement is out, the multi-tool's 3D jigsaw won't fit together as planned.
It's good parts. Sometimes it takes like 5–10 minutes just to check them, to make sure they're right.
Amongst the multi-tool's 17 tools and blades is a robust pair of pliers. For the pliers to work smoothly, workers must make sure that their jaws are perfectly aligned.
We're able to have it automated, that way it's a little bit quicker. It's pretty darn smart.
Lonnie must position the hole for the pliers' central rivet in exactly the right spot to make sure the pliers pinch objects smoothly.
We need really tight tolerances or else the rivet won't fit in all the way, or the jaws won't even open or close.
It's a crucial job that will make or break the pliers. To do it right, Lonnie relies on this innovative robot. It uses artificial intelligence to identify the orientation of each jaw, then delivers the piece to just the right place on the drill.
When the parts come down, they could be in any orientation or even upside down. In here, we have an eye that is able to check the orientation of the part and pick it up with the robot and insert it in and out of the machine. We're able to build parts much, much quicker.
Thanks to the intelligent robot, it's a simple job to rivet the two jaws together. Another robot grinds them smooth, so they're a perfect fit for the multi-tool handle. This multi-tool gives you razor-sharp blades in the palm of your hand, so each tool must have a dedicated safety mechanism. The hinges of the long blades click into tempered steel catches. On the other side, T-shaped tabs secure the bases of the shorter tools. And in the plier formation, hidden wedges push out a pin to lock down the blades on the inside. They release when you close the pliers, so you can get on with the next job. This ingenious pocket toolbox, 17 tools in one 10-centimeter handle, gets thousands of outdoor adventurers out of the tightest of spots. Why would you ever leave the house without it? The mighty car jack, the skateboard, the ATM, and the vacuum cleaner. What's inside isn't big, but it is clever. Next time you see one of these machines, remember, there's more to how things work than meets the eye.